Hello everyone, this is Joshua Kasiri and I'll take you through assignment 3 of my Mechatronics and Design course. And in this assignment 3 we are to come up with the real-time simulation of our earlier developed model for the robot. And the purpose of the robot was to give it a desired trajectory, and it has to move towards that trajectory. In this particular section, the rest of the components are still in software from here to here. It's only this part which is actuating with the real robot, as well as this other part which inputs from the real robot. So what is happening is, in this particular section, we are picking digital signals from the encoders of the right and left wheels, and we are getting that through pin 2 and pin 4 via the Arduino Mega. And then we have that signal coming into the right and left wheel encoded models that we design. If we can look into this, the encoder design has data acquisition, where we convert the incoming signal into an integer of 8 bits, and then we use that to calculate RPM. And then from RPM we get the rads per second. From rads per second we change it to velocity in meters per second, and this meters per second is what we feed into our system. Just to look into what happens when you're calculating RPM is that we delay the signal and we keep accumulating counts up to 100 counts, and then we feed these 100 counts, and then we get the sampling time, like how long it takes. We're using 0.5 milliseconds to get those pulses. Then we multiply them by 1000 and we divide by the actual PPR, that is pulse per revolution, to get per minute. These are just revolutions, so we have to change them in revolutions per minute by multiplying by 60. These were revolutions per second, yes. This 1000 is because of the millisecond that we actually put here, the 0.5 milliseconds. So here we convert it to seconds, and then divide by PPR, which then we convert it to RPM. Now going back, this is the setup of the encoder, and now that we've received the velocity from the encoder output, we feed these velocities. So now these become our actually measured velocities from the actual robot as it moves. So we capture them and we put them into an inverse kinematics model, which helps us to compute x, y, and theta of the robot, the actual robots. Then we feed them in as the measured values into our path controller. Just look into what the path controller is containing. So this is a pathway generator where it helps us get the trajectory, and then the incoming theta, x, and y measured values from the robot are fed into this to compute the errors which we feed into the kinematic controller. And then the kinematic controller, the purpose of it is to give us the final V of the robot and the omega of the robot. This is with reference to what it is desired versus what it is measuring. And then that is again converted into the corresponding velocities of the left and the right wheel, which then these are the new desired velocities that the robot has to move to so that it can achieve the desired coordinates. Looking into inside the kinematic controller, you will see that there is this A here, which I'll later on talk about how it is important in controlling the turning of the robot. Let's go back. So now that we have received the we've looked into the path controller, which gives out the desired velocities, then we feed these desired velocities into the PID controller for the motor velocities. Now this one picks the velocity which is desired and the velocity which is measured. Velocity which is measured is the velocity we picked up here from the robot, and then we feed them into the controller. And the purpose of the controller is to give us an output PWM signal that then becomes our new duty cycle for the wheel, so that it can turn a certain speed. And we tested this and it was working perfectly. Let me just show you some of the results that we received earlier. So these are some of the results. Just to take you through, we started by modeling the sensor selection and modeling, which is the incremental encoder, and then in that we modeled it. We're using Arduino toolkit as I've shown you earlier, and we got actually the right speed being 0.25 meter per second, as well as this is what I've shown earlier, the setup of the encoder. Then we went into some analysis of the model. In previous assignments, I discussed how this is the behavior of the model with this particular path. Now I try to change the path to see if we change the trajectory, if still it will work as expected. Yes, indeed, when we change just the trajectory without touching any um, variables in the controller with the desired trajectory, this is actually what the model gives. This is still in software simulation. However, when we went to real-time simulation, we have two different types, the hardware and loop simulation and control prototyping simulation. But with hardware and loop, it still doesn't give us the best accuracy. So we try to go for control prototyping, which would give us a more realistic simulation. Then this is how the setup was, the robot, and we're using Arduino to be like the controller for the entire robot, which helps us pick the inputs and also control the actuators of the entire robot. This is just a laptop, the laptop, which helps to do the software simulation and also visualize the journey moved by the robot. Yes, so in control prototyping, this is the setup as I've shown you earlier. And there were some observations that we realized in design optimization, of which we noticed that this robot earlier was moving so fast, a speed more than what we earlier agreed on. And then we had to adjust and have a better duty cycle. So we did like a small experiment that helped us know the best duty cycle to control our robots. And then we realized that 10%, which is about 25 over 255, will be the most sufficient duty cycle to help our robot move at the desired speed so that it doesn't move so fast and all. Yes. Now with our desired trajectory, so this is the new desired trajectory in the real-time simulation, the x and y plots plus theta from the response of the robot, and this is where the responses of the trajectory. This is the desired one, as you can see. However, this is what we got as the actual one or the measured one, and you can see that the final x here is 1.5 meters and the maximum y is 0.55 meters. However, here the final x is almost 1.45 and the maximum is 0.9. You can notice that there is a drift, especially because due to this arc at the start, that if it was not there, else maybe this would have fallen in range with where we want it to be. So we realized this, and earlier we noticed that there were so many issues happening due to the turning, and hence I tried to change the values of A. Remember the A I mentioned earlier, and then from different values we realized that the 0.06, basically as you lower A, it improves on the turning. So we realized that the most optimum one is 0.06, which helped the robot to have better and smoother trajectories. Then we again run another simulation on the same A value, but this is the second measurement. You can see that there's still some inconsistency in even the results being obtained, and then this helped me understand what could be the actual problem, and hence I tried to understand. And you notice that even in the second one, it's because of the turn being even bigger, it doesn't even reach the 1.45 mark. So meaning this affects so much of the turning, and it also affects the height. Yes, so this informed my research, and I went onto the hardware. When I looked into the hardware, I noticed that actually the robot had an issue with the left wheel, especially on the encoder. The left wheel, even if you give both the left and the right wheel the same PWM, they'll never actually they'll never move on the same speed. I don't know why, but maybe that is the main reason why, because this is caused due to the left turn. Because normally the robot is looking this direction or this, but it has a big sharp left turn, because at some point the left wheel is not moving at a required velocity, so it's like almost zero if this one is very low. So that's why there's a sharp turn. So that is why. And in conclusion, we realized that the simulation was really sufficient, and we moved the robot at 0.25 meters per second with the lowest accuracy of about 83% in the movement of the path. And hence we can improve this by working with the kinematic controller more, and then come up with a mathematical model that incorporates in the maximum desired velocity that can be used and make it as a reference for the robot as it moves. That said, let me take you through the demo.